We're now going to take a look at problem-solving tips for the diesel. So I'll again start by writing out the PV as well as the TS diagram. So those are the PV and TS diagrams for the diesel that we will refer to as we go through and take a look at tips in terms of problem solving. Now typically what you'll know with the diesel is you'll be given information such as the compression ratio, and you may also know the cutoff ratio for the engine. And quite often you'll also know atmospheric pressure and temperature, so P1 and T1. Now, if we look back at our process diagrams or schematics, and process diagrams, now the thing to note is 1 through 2, so from here to here, and then also, oops, I forgot to put 1 here, I'm sorry about that. These are isentropic processes, 1 through 2, and then again 3 through 4. So we can take advantage of that when we're solving problems. And the place where we can take advantage of that is we can use the relative pressure and relative specific volume in the tables in the back of the book. And so if we know T1, we can get the relative specific volume at that point, as well as the relative pressure. And from that, we can use these relationships . So we can use the relative volume and relative pressure as shown there. The other thing that may be known, or that we can use, P2 is equal to P3. If we look on our cycle, we'll notice that this is a constant pressure heat addition process here. So P2 is equal to P3. And we can also use the ideal gas relation that we looked at when we considered the Otto cycle problem solving tips. So quite often solving these problems is kind of like solving a puzzle. You have some conditions or some states, other states you don't have. So that is some information we can use, and then the next thing we're going to look at is the first law and how we can take advantage of the first law for solving these problems. So let's begin by looking at the heat addition process. Now if we look back at our process diagram, the heat addition is taking place up here going from 2 to 3, so that is our heat addition. And there we have constant pressure, and then for heat rejection we have constant specific volume. So that will have an impact on the way that we use the first law. So let's start with the heat addition process. Now I'm writing this for fixed mass. And remember, for the Otto cycle we looked at this boundary work term, and we were able to take advantage of the fact that heat addition was taking place at constant volume. Does heat addition take place at constant volume now? And the answer there would be no. Because if you look here, this is state 2, that's state 3. We're changing the volume going through the combustion process, and consequently we cannot make that simplification that we did for the Otto So dV does not equal 0. But what we can do, we can use the little trick that we had for the first law whenever we have moving boundary work, and that is we can rewrite the first law in terms of enthalpy, and that will include boundary work. So that's how we handle heat addition when we're changing the volume, because we're doing boundary work during the heat addition process. Now for Q out, let's take a look back at our process diagram. This is where we have the heat rejection. So here, there is no change in volume. So for the heat rejection process, we do have the fixed volume, and so then when we write out the first law for a fixed mass, we can reject that work term because there's no boundary work, and so what we're left with is Q out is U4 minus U1. And so those are the two equations that you can use for handling the heat addition, and then finally the net work is just Q in minus Q out, like it was for the auto. So sometimes that can be confusing for students why they're using enthalpy in one part of the cycle and then internal energy in the other. And the reason is because one, the volume is changing, and so you need to include boundary work, and then the other part for the heat rejection, the volume is not changing, and consequently you can use your internal energy for that part. So those are some of the problem solving tips that you can use when you're working through problems involving the diesel power cycle.